Bigger is better, at least when it comes to telescope mirrors. But larger mirrors have to be thick so that they don't deform under their own weight. And really large mirrors deform anyway, no matter how thick and heavy they are. The solution? Thin, lightweight mirrors and a magic trick called active optics. And this is the state of the art. The mirrors of the Very Large Telescope, the VLT, are 8.2 meters across, but only 20 centimeters thick. And here's the magic. A computer-controlled support system ensures that the mirror keeps its desired shape at all times, to nanometer precision.
In the middle of the Atacama Desert, ESO created an astronomer's paradise. Of course, the unique selling point of the Very Large Telescope is its unequaled view of the universe.
Without thin mirrors and active optics, the VLT wouldn't be possible. But there's more. Stars appear blurry, even when observed with the best and largest telescopes. The reason? The Earth's atmosphere distorts the images.
Enter the second magic trick, adaptive optics. On Paranal, laser beams shoot out into the night sky to create artificial stars. Sensors use these stars to measure the atmospheric distortions, and hundreds of times per second, the image is corrected by computer-controlled deformable mirrors.
And the end effect? As if the turbulent atmosphere were completely removed. Just look at the difference.
Get him up here. You think you got what it takes? Can you keep up? Let's go, motherfucker! Come on!
I appreciate you saying that because, you know, I'm not a gay woman, you know?
Yeah.
And it's that, you know, touchy sort of subject, right? Where can you stand up for people that you are not necessarily fully part of that community in a way that you can understand what you all go through, right? But I have always been surrounded by incredibly intelligent, powerful gay men who have lifted me up through lots of changes in my life. Becoming famous was very strange, and it's the gay men in my life that helped me to become a woman. And I don't know that a lot of people would understand that, but it's because of what you've been through. You have survived so much that you inspire me to continue surviving.
If you ask 10 physicists what a particle is, it would not be surprising to get 10 different answers. In my previous video, I talked about how light comes in discrete packets of energy called photons. We learned that these photons act as both a particle and a wave. This is the wave-particle duality of nature. Quantum mechanics revealed via the Schrödinger equation that all quantum objects should not be considered particles, but more like waves smeared out in space. They are described by a mathematical term called a wave function. This function describes the state of the object. It doesn't tell us where a particle is, but only the probability of where it might be if we measured it. The wave function tells us that what we call a particle is spread out over space until the moment we measure it. And as soon as we do, the wave function representing the particle suddenly collapses so that it's not spread out any longer, but is localized around a distinct point. The double slit experiment is the classical example of this collapse. If we send one photon at a time through the double slit thousands of times, we see a wave pattern. But if we stick a detector at the slit to measure which slit the photon is going through, we get rid of the wave pattern. The wave function has collapsed. Why does the wave function, which is a mathematical expression describing the probabilities of a particle, suddenly collapse upon measurement? Why or how this happens is not well understood and is known as the measurement problem of physics. So we have something that could best be described as a spread out wave prior to measurement, but after measurement, we get a delta function, which has a spike like a localized wave. This is something representing more like a particle. So is a particle just a collapsed wave function? Perhaps. But this leaves us with more questions than answers because we don't really even know what a wave function collapse means. As you might have surmised, it's not that simple to answer the question of what a particle is. And if you ask a physicist, he might just go straight into the math, describing a particle. And the answer he may give you could be purely in mathematical terms. But the world we are in is physical. Math is just a tool used to describe the physical reality. If pushed for something more concrete, some physicists will just tell you that particles are simply those objects that we detect. But these answers are deeply unsatisfying. So let's not do that, and instead, let's look at what the current best description is based on what we know. What we have learned about particles from quantum mechanics is that we can consider photons in terms of a wave packet. This wave packet can be looked at as a kind of particle, and something similar can be done for describing other particles as well. But their wave aspect smears out their properties, like position and momentum. The Schrödinger equation works quite well in describing the wave nature of quantum objects, but it has some limits. It does not account for special relativity. This happens specifically when the velocity is close to the speed of light. In order to account for relativistic effects, space and time have to be treated equally. But if you look at the Schrödinger equation, you'll see that time and space are not treated equally. In the 1930s, scientists realized that one could get an even better formulation of quantum mechanics than what physicists like Schrödinger achieved by considering quantum objects in terms of quantized fields. When this is done, the equations of quantum mechanics could be modified to account for special relativity by treating space and time equally. This led to quantum field theory. In quantum field theory, what we call particles are quantized waves in a field that spreads throughout space-time. The idea of quantized fields was a necessary step in order to describe objects like photons and other fast-moving objects that demand to be treated according to the rules of special relativity, which starts to have a significant effect at or close to the speed of light. Quantum field theory is nothing but a theoretical framework that unites ideas from classical fields, special relativity, and quantum mechanics. The idea is like this. You start with a field, or analogously, picture yourself a calm sea. This is an empty field without any particles. This is our starting point. It may sound a little bit weird, but stay with me here. Imagine that this field or sea stretches throughout all of space-time. Note that this would be in 3 dimensions, but for visualization purposes, we are representing this in 2 dimensions, like the surface of the ocean. Now imagine that there is a wave in the sea. This is a particle in our field. Then there can be another wave, which represents another particle. In the field, each particle is an excitation of the field, just like a wave in the sea. Because we are considering our particles as waves, if we collide them, the particles collide like waves, just as in the double-slit experiment. There is, however, at least one difference between the quantum field and our ocean. Our ocean is not quantum. For our ocean field to be quantum, we have two requirements. First, the waves in our sea must have some discrete magnitude, because in quantum mechanics, things have discrete quantizations. This can be represented by the amplitude or height of the wave. Let's say the wave can be 1 meter, 2 meters, 3 meters, and so on. Each meter corresponds to the number of particles in any one place. But there's a second requirement too. A real quantum field is never calm. It always has some minimum energy state. So we will say that the 1 meter wave represents this minimum energy state of the field. The minimum energy of 1 meter is called the vacuum energy. It means that for a real quantum field, empty doesn't mean nothing. There's still something, some minimum energy present. Then each extra meter of amplitude or height is a real particle. Now, the interesting thing about quantum waves is that we can only create taller waves in increments of whole meters. So if we don't have enough energy to add at least 1 meter to the wave, then we won't have any change to the wave at all. In other words, there can be no 1.5 meter or 1.75 meter or even 1.9 meter waves. Only 2 meters, 3 meters, 4 meters, etc. So our quantum field is full of these minimum 1 meter waves, and each extra meter is then a real particle. But we can only create these taller waves if we have enough energy to reach the next meter. If there's not enough energy to reach at least 2 meters, no taller wave is created. The 1 meter waves are from the quantum vacuum. They represent the non-empty minimal state. These quantum waves slosh around, and in some places, there might be momentarily enough energy to create a large 2 meter wave or a particle. But then, almost just as quickly as it's formed, the particle vanishes again in the sea of fluctuations. These are analogous to virtual particles that come in and out of existence all around us, but are undetectable because they last for too short a time. Since virtual particles cannot be directly observed, they only exist mathematically. However, they do result in other effects which can be detected, namely the Casimir effect, which happens due to a pressure difference caused by the virtual particles between the inside of two plates and outside of the plates. This is a unique effect supporting the idea that the universe consists of quantized fields rather than just quantum mechanics. The quantum field is like the sea. It's the background on which waves appear and disappear. And just like energy can create waves in the sea, energy added to the field generates particles, which we can observe. So in quantum field theory, we have a field that is never still, never empty, and we can create a particle if we have the exact amount of energy needed. But still, you should keep in mind that this is just a mathematical construct that appears to fit reality. If you expand this concept to other particles, we have to imagine other seas on top of seas representing a different field for each fundamental particle that we know of. So there would be a sea representing the field for electrons, for example, a field for photons, a field for quarks, etc. This concept led us to where we are now. We have this general theory called the Standard Model, in which we include all known fundamental particles. And we assign individual fields to each type of particle. Now, what does fundamental in the word fundamental particle mean? From a mathematical point of view, it means that the particles of the Standard Model are the smallest particles from which we can construct the world around us. There is nothing smaller that we know of that these fundamental particles are made of. This brings the circle back to Democritus and the search for the minimal unit or particle of the universe. That's what we mean by fundamental. They are the most fundamental particles, at least for now. You have to remember that one time we considered the atom to be the smallest fundamental particle. Then we discovered the electron and proton, and later even smaller particles like quarks that the proton is made of. So maybe we shouldn't be so confident that we have really reached the ultimate fundamental level. What's more, the word fundamental really doesn't tell us a whole lot about the particle. In fact, we can't even directly detect all these particles. For example, quarks can never be observed as free particles. So these cannot be confirmed with direct observation. And for the particles we can observe, what we really see is an energy signal in our detectors, not the particle itself. So should the definition of a particle be an energy signal in our detectors? Perhaps, but I think we can do a bit better than that. As of now, the best description would be something like this. A fundamental particle is an excitation in a quantum field that is constantly in flux. There are at least as many fields as there are particles in the Standard Model. Each particle can propagate in its field. The interactions of these fields and exchange of energy results in particle creation and annihilation.
If an atom were as wide as your arm span, then the electrons would all be whizzing about inside the volume enclosed by your fingertips. Meanwhile, the nucleus would be sitting in the center, and its diameter would be smaller than the width of a single human hair. So all of the atoms that make up you and me and all the seemingly solid things in the universe are mostly empty space. Now this is incredible, but what is even more mind-boggling is that empty space is not truly empty. I know because I've seen it. This is a simulation by Professor Derek Lineweber at the University of Adelaide. It was made using a supercomputer to crunch the calculations of quantum chromodynamics. Now that is the theory of fundamental particles called quarks, the building blocks of protons and neutrons, and how they interact with each other through gluons.
What you're looking at here is the energy density of the gluon field fluctuations. Where the little red spots come out, the energy density is very high, and it fades down through the colors. So in the lowest energy field fluctuations, I'm not rendering this animation so that we can actually see into it.
And what we see is a bubbling soup of quantum field fluctuations that come and go incredibly quickly. Now the theory that describes quarks and their interactions with each other through gluons is called quantum chromodynamics. And chromo is the Greek word for color. So in some way these objects are meant to carry the color charge. But they are much, much smaller than the wavelength of visible light, so there is no way that they are actually colored. But it's a useful analogy that helps us think about how they interact and the particles that they can make up. Now the rules are pretty simple. In order for a particle to exist, it must be colorless, or white, like this house. Now you can accomplish that in two different ways. You could make 3 quarks where each one is a different color, red, green, and blue, so overall they combine to produce white. Or you could use a quark and an anti-quark, where one is a color like green and the other is its anti-color, say magenta. Now what I'd like to do on this little patch of beach behind me is simulate how quarks actually bind together and form different particles. Now for this you need to remember that in the last video we talked about how empty space is not truly empty. So the beach here has these undulations in it which represent the fluctuations in the gluon field. But you have to imagine this beach sort of rippling and these bumps coming and going. Now that's really important because to get rid of those fluctuations actually takes energy. And this is an important part of binding the quarks together. The existence of quarks actually suppresses the gluon fluctuations and creates what's called a flux tube, an area where there is really nothing in the vacuum, and that's in between this quark and the anti-quark, and that pairs them up and creates what's called a meson, the quark-anti-quark pair. What's interesting about the flux tube is that as these quarks become more separated, the flux tube remains the same diameter and the same sort of depth of suppression of the field, which means that the force doesn't actually increase. It's not like a spring, it's not like an elastic band. The force is the same that is pulling these quarks back together. But you are putting more work in as you move these quarks and anti-quarks further apart. And so for a time people thought, well, these quarks are always going to be confined, however far you move them, you're just going to get a really long flux tube. But what actually happens is that you put in enough energy that you can actually create a quark-anti-quark pair.
Nevertheless, the quarks are still confined. You can never see an individual quark, because if you try to pull it out, you'll put so much energy into the situation that another quark-anti-quark pair will be created.
Now to form a proton, we're going to need an up quark, another up quark, and a down quark. Now the standard model of a proton that you've probably seen involves these quarks bounded together by little gluon springs that go between them.
We know that that picture is totally wrong now. Even in the best sense, you might have hoped that you would see flux tubes around the edge of the triangle, but we know that, in fact, they don't do that. That you get these Y-shaped flux tubes.